Hello, 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 everybody, and welcome back. We're looking at question number 24 now of the 2008 Cayley math contest. A cube has edges of length 1 centimeter and has a dot marked in the center of the top face. The cube is sitting on a flat table. The cube is rolled without lifting or slipping in one direction so that at least two of its vertices are always touching the table. The cube is rolled until the dot is again on the top face. The length in centimeters of the path traveled by the dot is. Okay. So, this is a three-dimensional geometry question, and you might just have a little trouble visualizing what's going on. Now, I have all these cubes behind me. Let's pick a nice, simple one. Here we go. So here's a Rubik's Cube I picked up. It's a university stress hotline for students. But I mean, if you have little wooden cubes or something, you can get a pencil mark in a dot on the top, just to imagine what's going on here. Okay, and I'll sort of use my little bamboo tablet. So we sort of start here, and how exactly are they moving it? I'm keeping these two corners down here, and I'm just rotating it that way, and we flip, and we flip. And we flip, and then, the dot, or the logo, I guess, on the other side is back on top. So we can sort of see, well, you're going to flip once, twice, 3 times, 4 times, and you're back on top. But more than that, you can actually see, well, how is this dot moving? It's sort of, if we imagine these corners here as sort of a pivot, sort of a circular arc. And this can give us a good idea. Now, this isn't giving us math to do. Put this guy back. But this is giving us a way to visualize that. And with a three-dimensional problem, sometimes visualizing is half the battle, really. Okay. So we sort of understand what's going on. We can move over to our notepad and imagine it a little better. So we get our flat top. Well, maybe we can draw it a little flatter. There we go. Draw it a little flatter. As, good, not great. So our cube, we'll just look at it from the side, just like I did. So we've got our cube. We'll start rotating it, and so these dots here will pivot, or these vertices, and then so we'll imagine our dot is here. So now after rotating it, and so we rotate around these dots. This becomes a fixed point. What happens to the dot in the center? Because that's what we're asked. Well, how far does it travel? I guess. So it travels. There we go. And so you have to ask yourself, well, what's going on here? Because it's going to be the sort of the same motion each time. Now we're going to rotate along this dot. And so now, each time we sort of have to ask ourselves, well, what's going on with the dot? And each time it's going to be a right angular arc that it travels through. Why is that? Well, when the cube rotates from one position to another, it's rotating a full quarter twist, or 90 degrees, a quarter of the way around a circle. So now we rotate again. And what happens? Well, we connect our dot up to our new center, and it rotates till it's up on this side here. And then finally, the last rotation with these new corners here, that's our new center. Well, connect the dot up there, and we're around the point we're rotating. And we know where it's going to end up, so it's not really a problem for us to draw that. We get another quarter circle. So the total distance that the dot that we're talking about travels is perimeter of a quarter circle, perimeter of a smaller quarter circle, perimeter of another quarter circle, and perimeter of a big quarter circle. Again, the question is, well, what are these quarter circle perimeters? Okay. Now, we know that the side length is 1 centimeter. Okay. And the dot is positioned, I believe they said halfway. Dot marked in the center of the top face, so it would be halfway. So it's 1/2 a centimeter this way, and so if we just sort of enlarge this area, here's the dot, here's the pivot point, 1 centimeter, 1/2 centimeter. We can figure out that this is root 5 over 2 centimeters. Okay, and so, well, what's the formula for the perimeter of a quarter circle of radius r? Well, what's the circumference of a circle of radius r? 2 pi r. We want a quarter of that, so we divide by 2. So it'll be pi by 2r. So this first distance that is traveled, the radius is root 5 over 2. So it'll be root 5 over 2 and then pi by 2. Okay? And it'll be the same distance here because it's still a half and then a full centimeter. So it's still root 5 over 2 here. So we have sort of 2 copies of that. And there'll be 2 copies of both things. So we'll get pi root 5 over 4. And then what about in here? Well, we can see these quarter circles here have radius 1/2. So the perimeter is going to be radius is 1/2 times pi by 2. So it'll be pi by 4 when we simplify that. Okay, and now the 2 can come along. I'm going to switch back to black here. The 2 comes along, cancels out with parts of the 4, and we'll take out a factor of pi. We'll get root 5 plus 1 all over 2. Oh, isn't that nifty? That's the golden ratio, 1.618033989. No, didn't use a calculator for that. If you're wondering, I just am very familiar with that number. Okay, so is this one of the possible answers? Yeah, it's the really interesting looking one here at the end. It's E. Okay. Do note this root 5 pi here. I think this would be if you just drew one picture and assumed, well, it's going to be exactly the same motion, the same sort of arc, and you just multiply this guy by 4. But you do have to investigate a little bit further. It's the same type of motion. It's quarter circle motions all the way around, but the length of the quarter circle, and therefore its perimeter, changes a little bit. Okay, so that's answer E, and that is the second last question, all done. Fantastic, we're moving right along. I will see you guys for the next question, the last question, question 25, in the next video. Thanks for watching.